Hi everyone. My name is Haofan. I'm a PhD student advised by Owen Arding. And today I'm going to give my advancement talk. And my topic is building secure distributed applications. Before directly jumping to the core content, and let's take a look at this scenario. Alice, who is a service provider, so she has electricity billing service that can raise the electricity meters from the user and bill to the customer. However, she doesn't have the hardware resource to host these applications. So she reached out to a cloud provider, Bob, to rent some machines or servers to host these applications. And Charlie is one of the users of this building service. So is this system secure? And what could happen to these applications? So first, the application may send the data to a third-party contractor for additional processing. However, the user may not know about this, or they may not know what is actually sent to the third-party contractor. And the similar issue actually happens in the reality. For example, some people may trust Apple, but they may not trust the third party that they're doing the additional processing. And or the Alice may hide a backdoor in the applications to collect users' privacy data and sell it to Trudy, who is an attacker living in the dark web. Or Trudy may directly hack into Alice applications and retrieve users' sensitive data. And this kind of case happens even more frequently in the reality. So all of these cases violates the principles of confidentiality. Or in other case, the cloud provider may also be a user of Alice service. So and he wants to enjoy the electricity for free. So he may log into the backend service and tamper with Alice applications so that his bill always has much lower cost. And this attack violates the principle of integrity. Or in other case, Bob may also host a building service, and in order to compete with Alice, he may try to randomly suppress the message sent to Alice applications. And therefore, customers using Alice service may have worse experience, or while Bob's customer may have a better experience. And this attack violates the principle of availability. So based on the given example, what defines a secure applications? First, we want our sensitive data kept in confidential. And we also need to ensure both code and data are untampered. And servers and data are available when it's needed. So our goal is the combination of all of these three principles. And that's also the famous three principles of information security. But who do we trust to enforce all of these three principles? From the view of the user, Charlie, he may think that Alice and Trudy and Bob and even the applications are malicious. Well, in terms of Bob, he may also think that the users and service provider and attackers are malicious. While Alice may think that the users and the cloud providers and attackers are malicious. Therefore, our philosophy is to reduce the trust on all of these entities and shift this trust to the application's code. Therefore, all entities can focus on what is the code doing and what is the system doing, and if the application is doing something good with us or not. However, in realities, we often rely on all parties that obey the terms and conditions or the contract. And hopefully the law enforcement will punish the violators. And this creates the deterrence for violators that violating the rules. And it's a group protection mechanisms, and we still want it to be there. But it is not 100% perfect, because once it's violated, there's no way to undo the damage. So is there any technical tools that can solve the problem from fundamental, so that we need prevention mechanisms that attackers has no way to violate the rules? So how about using end-to-end encryption? The users encrypts the data before uploading to the server. And even though the user can doing the computation locally, the server only sees the data in encrypted form, and doing the computation over encrypted data will only generate a meaningful result. And talking about computation on encrypted data, there's actually a technique or algorithm called homomorphic encryption. So homomorphic encryption allows computations on top of encrypted data. For instance, the server can compute over the encrypted data to generate a result also in the encrypted form. And all of these data are still unmeaningful to the server. But this time, if we feed back this encrypted data back to the client's encryption algorithm, then the client will be able to obtain a meaningful result. But meanwhile, different operations like arithmetic computations and comparisons may require different encryption algorithms. And thus it will make the application even more complicated. In addition, attackers may still tamper with the computation to generate a malicious result. And to address this issue, there are still ongoing research about verifiable homomorphic encryption. Another option is multi-party computation. So in multi-party computation, the secret is split into multiple pieces and then sent to multiple servers for computation. So even for basic arithmetic computations, we still need to split the secret into multiple pieces and ask several servers to run the computation. And another important point about multi-party computation is that by combining multiple pieces, the attacker will be able to get a complete secret. So so we need to prevent the attacker to obtain multiple pieces of the secret. And in the previous example, Alice has to rent multiple servers from multiple cloud providers, and that's even more expensive. Additionally, multi-party computation can provide some levels of availability depending on the protocol and number of replications. But our choice is enclave. The enclave is a cryptographically protected memory region that contains both code and data. And it also provides a verifiable remote execution environment. The enclave is cheaper than the aforementioned approaches, and it provides no availability. And we will provide our solution in a later slides. Also, by using enclave, we have to trust the manufacturer, the CPU manufacturer. This may not be an easy requirement since, for a manufacturer like Intel, there are already a few known attacks that are related to the private key of the enclave. But since enclave is still a novel technology, so in this work, we assume that we are building the framework on top of a well-developed platform. But what exactly is enclave? So inside the CPU package, there's a unique secret key, and it's used for the encryption and decryption. And in the memory, there's a reserved region. And when reading the data or code from this reserved region, it will first be decrypted by the CPU and then sent to the operational unit. And when the computation is done, the result will be encrypted again and written to the memory. That means only the CPU package knows the secret. And anything that leaves the CPU package is in an encrypted form. In addition, enclave also provides a verifiable remote execution environment. The users will first measure or calculate the hash of the enclave binary. And then this enclave program is deployed to the remote enclave platform. And in the remote enclave, the CPU will perform a measurement to this application, and then generate its hash. So by comparing this hash, the user can be sure that the program deployed in the remote enclave is the one that he actually deployed. And additionally, the CPU's key is endorsed by the CPU manufacturers. This forms the chain of trust, where the root of trust is the CPU manufacturer. And this process ensures that the enclave application is actually deployed to a real enclave platform instead of a fake enclave platform or a simulation environment. And this process is usually called remote attestation. So now let me introduce the decent framework. Let's first review how remote attestation works for Alice building app. The user knows the hash of the building applications, so it will perform a remote attestation to the building app. If the verification is done successfully, it will then send the secret data to the building app. But now let's assume Alice's business is growing bigger, so she wants to scale out applications into a data processing component and a building component. So without relying on external source, how do the two components verify each other? We may first think that they can embed each other's hash and compare them during remote attestation. But will that actually work? So let's start from the code. We first build the data processing code into the enclave binary, and then we measure the hash and then embed this hash into the building codes. And we compile the building code into the building enclave, and we do the measurement on the building enclave to generate the hash of the building enclave. And now if we want to embed this hash into data processing code, we have to recompile the data processing enclave again, and which will result in a different hash for the data processing enclave. So we notice there's a circular dependency issue. A strawman solution could be embedding the hash of the building service into a data processing service. and let the building service load the other hash afterward. But the question will be who gives this hash so that we can trust its authenticity. Some existing work suggests that we can have a trusted third party to distribute this hash during runtime. But now we not only trust the code, we also have to trust this entity, which could be a single point of failure. Another existing work suggests that we can combine every components into one enclave binary, and having a switch to activate different part of the enclave. This approach seems to work, but what if we scale out the application even more? Mm-hmm. So this is a microservice architecture from Uber, and there are a large number of components, and they all maintain separately. So if we use the aforementioned technique, we will be having a gigantic binary for each node. And if we want to update any single component, we have to recompile everything and deploy the code to all the nodes. And moreover, the microservice architecture may have large number of replications for each component. And each session tends to have fewer number of requests. So the lifetime of each session is relatively short. So this will lead to more remote attestation process. However, remote attestation isn't just one message between two components. Instead, in HGX EPID remote attestation protocol, there are multiple messages sent back and forth between two components, and it even involves Intel attestation service. This will create a huge overhead during the remote attestation process. And last but not least, in the real-world applications, they are updated frequently. So how to let all components knows the hash of the new component? So in summary, to build a distributed enclave applications, we want to address the mutual attestation issue and provide a low overhead remote attestation protocol for each sessions. And we also want to enable dynamic authorization of new components. So let's first see how we address the mutual attestation issue. So previously we mentioned the circular dependency problem makes the mutual attestation issue difficult. And one option we have mentioned is to load the hash after the build time. Now let's see what could go wrong in this solution. The client knows the hash of the data processing component. So it verifies the data processing enclave and then sends the sensitive data to this enclave. Ideally, both data processing component and building component will load in each other's hash, so they can verify each other during the runtime. But it turns out that the data processing component actually loads in a malicious hash of a malicious building X service, but the user doesn't know about this, so it still sends the secret data. And now the data processing component leaks the data to a malicious building X component, and which is then leaked to the attacker. To address this issue, a low-time auth list is required. The auth list is a mapping from the hash of the enclave to the name of the enclave. So everyone in the system should agree on the same auth list. And once it's loaded, it cannot be changed. So in this time, a malicious building X service may pretend to be a legitimate building service. But the data processing component will detect that it has a different hash than the one stated in the auth list. So it will refuse the connection. or the host may collude to provide a malicious auth list. And so even though the data processing component and building X component can communicate with each other, but now the client noticed that the data processing component is having a different auth list, so the client will refuse the connection. The next issue we want to address is the remote attestation overhead.
Can I just interrupt you for 1 second? I just have a clarifying question. Can you go back to the last slide? So one of the straw men that you considered was building all of the binaries and sharing them all everywhere, and you showed how that didn't scale to something like a microservice architecture. And I totally buy that. In fact, like, you know, it's not just about the fact that things update, but the things update at different rates, and so it wouldn't be tractable to keep reshipping the binary. What's happening in this auth list situation is that you've created these manifests, and the manifests are identical everywhere. Aren't you doing the same thing except for the metadata rather than the data? And don't you run into the same issues around, you know, I've got this huge microservice, it's got hundreds of services. Every time there's a tiny change to one of them, everyone needs to update all of their auth lists. You've reduced the overhead of doing so because we're not actually shipping the code. Is that is my understanding correct?
That's a very good question, and we actually provide a solution in a later slide.
Great. So you're building up your strong. Okay, thanks.
Yeah.
So sorry.
So the next issue we want to address is remote attestation overhead. So in the previous slides, we show that in remote attestation protocol, there are many messages between two components and involve the IAS service. So the idea is that since the similar report is generated over and over again, is there any way that we can preserve this report and so that it's reusable and verifiable to a third party? The answer is self-attestation. So during programs initialization phase, the decent server will generate a unique key and perform a remote attestation to itself. So this will bind the remote attestation report to this unique key. And then we encapsulate this report and the key into a certificate. And then we can use this certificate during the TLS handshake. And the decent components are the actual components of the applications. It also generates its own unique key pairs, but it performs a local attestation to the decent server. So this demonstrates that both decent server and decent components reside in the same enclave platform. And then the decent server will issue the certificate to the component. And this forms the chain of trust, where the root of trust is still the remote attestation report. By using this design, we only required one remote attestation report per node. And now let's see how the self-attestation works with auth list. So first, the decent server perform a remote attestation to the IAS to generate a remote attestation report. And then the decent components loads in the auth list, and then it will perform a local attestation to the decent server. And so that it can obtain the certificate chain. And then the client will use the TLS handshake to verify the self-attestation certificate chain and the auth list, and also the remote attestation report inside the certificate. And if the verification is done successfully, the client will send the secret data to the decent component. The host may still collude to provide malicious auth list, but this time the client will detect that they are having the different auth list, so it will refuse the connection. To ensure the correctness of decent protocol, we formally verified our protocol with ProVerif. So ProVerif is a verification tool for cryptographic protocols, and attackers may manipulate any data and read any data on channels. And they can also create messages that derived from any obtained materials. So we successfully verified the two security properties of decent protocol, including secrecy and authenticity. To evaluate the expressiveness of decent protocol, we built the ride-sharing application. And this application is built based on the microservice architecture from Uber. And the successful communication among 6 different nodes shows that decent protocol can handle a complex applications that has multiple components. To evaluate the performance of decent protocol, we implemented decent HT, which is a decentralized encrypted key value store based on core. And we then set up the YCSB benchmark over decent HT, and we test the performance for the enclave with different session lengths. And then we compare the performance of decent RA to 3 different groups. The SGX RA groups are only using the standard SGX EPID remote attestation protocol. And the 2 TLS group use the same decent RA protocol, but outside of the enclave. And the result shows that decent RA provides a significant higher throughput in short sessions. And while SGX RA requires have to process more requests per section in order to compensate the cost of the remote attestation overhead.
So sorry, I just want to stop you for 1 second. Go back again. Can you just headline this for us? So the red line is like how typical n squared attestation would work without your without your improvement.
Yeah.
And the TLS and sealing, that's kind of the best you could hope to do. And you're showing that
these 2 lines are the TLS groups which are using the same decent RA protocols, but outside of the enclave.
Gotcha.
Yeah, it's outside of the enclave. So this difference, you can see the overhead of the enclave.
Gotcha. So there isn't really a baseline, the best you could do, but this is sort of your baseline overhead. And gotcha. Thanks.
I also have a question. What do you mean by throughput here exactly?
The throughput means number of requests per session, per second.
That can be taken care of, that can be attended?
Yeah, they can be processed by the enclave program.
And then the request per session is what exactly?
Yeah, so each session so we are doing the benchmark on the decent HT applications. So it's like a key value store. So each session means that it will perform a remote attestation first with the DHT server, and then it will send the request to either reading a value or write or update a value to the remote server. So the longer the session is means that, so for example, we do the remote attestation first and then perform 100 request, and then a longer session means that we do the remote attestation once and perform maybe 500 or even more requests in this session. So for the decent RA case, its performance is better if the session is short, meaning that there are fewer number of requests in each session. But for the standard SGX RA protocol, because the overhead is too big in the remote attestation phase, so it has to do more process, it has to process more requests after the remote attestation in order to compensate the cost. Is that clear?
Yeah, thank you.
Yeah, that was an important clarification, because I just assumed that the x-axis was as you were increasing concurrency, but actually what you're doing is you're amortizing the cost of the attestation over requests. So you're mixing a couple things here. I guess one other question, and I don't want to slow you down too much, is do you have a hypothesis for why the maximum throughput of decent RA is not as high as that for SGX RA?
You mean
why do they cross at 1,000 requests per second, and why does SGX RA attain higher maximum throughput?
Yeah, so the difference is that in the decent RA we are using the TLS, the standard TLS protocol from the embed TLS library, while in the SGX RA we are not using the TLS protocol, and instead we are using the protocol that's suggested in the sample code, and I noticed that in the TLS protocol there's a bit more metadata that's sent between the client and the server, so that might cause the difference in here.
Gotcha. Thank you.
Yeah, so our solution to the confidentiality and integrity is using enclave. So now let's talk about dynamic authorizations. So previously we proposed to use auth list to address a mutual attestation issue. But how to update the components? So far, the only solution is to revise the auth list and restart the entire system, and this will cause the system downtime. And in modern applications, we want to avoid system downtime. So we need dynamic authorization. To dynamically authorize new components, we use a verifier, which are designated entries on the auth list. So in general, the verifier has two tasks. One is the first is verifying and then authorize the new component. So during the verifying step, the verifier needs to ensure the new component is trusted to be added to the system. So the verification scheme is application dependent, but we provide the API to accommodate the application's needs. For example, verifier can collect votes from stakeholders, or they can directly verify in the code. And after that, the verifier will issue a certificate to the new component. And then the new components will use the new certificate to join the system. And in the previous slides, we mentioned we can use verifiers to collect votes from stakeholders. But record our design principle that we want to reduce the trust on people as much as possible. And clearly, the idea of stakeholder actually go against our ultimate goal. So And in some applications, it's hard to find a small group of stakeholders that are trustables. And even we do find this group of people, they are still potential to be corruptible. So so we want to avoid the idea of stakeholders, but how to avoid it? So now let's open the black box of this the idea of stakeholder and see how they may act inside this black box. So first, the developers will submit the new components code to the stakeholders, and the stakeholder will verify the code and submit their votes to the verifiers. However, stakeholder may not just read through the code and say yes or no. They may have some kind of rules or specifications or standards that says what kind of new components are satisfied and what others don't. So if the new components satisfy their specifications, they will sign approvals and send the approval to the verifiers. But let's say the code base can be very large, so manually checking the code is still error prone. So then they may seek for some help from a formal verification tool. And so that they give the new components code and the rules to this formal verification tool, and these tools can tell the stakeholder whether or not the new code satisfy these rules or not. So if it satisfies the rules, the stakeholder will sign the approvals and send the approval to the verifiers. But now in this stage, do we still need stakeholders? So therefore, our idea is to have a formal verification tool that built it inside enclave, and this enclave will accept the new components code and the specifications, and to verify these new components code. And if the new code satisfies the specifications, it will sign the approvals and sends the approval to the verifiers. There are several existing works that can verify the information flow control property of applications code. But all of them are outside of the enclave. So for example, GIF or Java information flow can check the information flow control of the Java code, and they requires the labels on the each variables and the function calls, function prototypes to verify their properties. And the fabric is built based on GIF, and it also provides some mobile code features so that we may load code from an unknown external source. And the fabric will be responsible to verify the IFC properties, and it will only execute the code if it satisfies that property. So our goal is to verify the confidentiality and integrity of the given code. And we also want to provide a blueprint that allows developers to verify even more properties like correctness of the application. So ideally, each component will have an entry point function that has both return type and parameter type labeled with the confidentiality and integrity property. And the verifier will check the code against this function prototype to ensure they are consistent. And now let's see how these work together. So First, the decent JVM loads in the Java code and the auth list. And then it will send the code to verifier for verification. And if the verification finishes successfully, then the verifier will issue a new certificate to the decent JVM. And then the loaded code can use this new certificate to communicate any existing components. And so far, we still haven't answered how we're going to achieve availability. So let's see our solution. So to answer these questions, let's first review the what is blockchain. So the blockchain is a append-only log that and each log is operations that update some state. So for example, let's first assume both Alice and Bob has $100 in their account. And a block said that Bob paid Alice $50, and so that we update the state accordingly. And a new block says Alice paid Bob $20, so we update the state again according to this new block. And the blockchain and its state are replicated to many nodes in the network. And if one node is down, we can easily connect to the other node. So this ensures very high availability. So can we simply combine these two to achieve all three guarantees? A technical report from Microsoft's research proposed that we can combine the enclave with a permission-based ledger. And in the permission-based ledger, each author is authorized to publish new blog. So so if an application that has some group of stakeholders, then we can easily adopt this framework. But remember our design principle that we want to reduce the trust on peoples and stakeholders. So in that case, we want to use a public blockchain. So most of the public blockchain like Ethereum are using proof of work protocol. So instead of authorizing users to publish blog in the public blockchain, any users that has computational power can join the network and publish new blog. And but they have to solve hash puzzles to determine who can publish the next blog. So anyone that solve this puzzle can publish a new blog to the blockchain. And the time used to solve this puzzle is called block time. And ideally, we want to maintain a stable block time. For example, it's around 12 seconds in Ethereum. So if the new block is generated too fast, we don't want to increase the difficulty so that the next block can be generated in a slower speed. And in the other way, if the block is generated too slow, then we want to decrease the difficulty. So the nodes can generate the next block faster. But the problem is in public blockchain, anyone can publish a new block, and that can cause the issue in enclave. And but let's see why it can cause an issue. So we use this graph to demonstrate what is enclave. And now let's consider that the enclave needs to communicate with some node in the internet, or they need to download the blockchain from the internet. So how can they do? Obviously, the CPU cannot help the enclave to establish a network connection. So the only way is to ask the host operating system for help to establish the network connection. And however, the operating system is under the attacker's control. So we cannot trust this network connection. And let's see what could go wrong in this scenario. One possibility is that the attacker can suppress or delay the message from the network, or the attacker can just generate its own malicious blockchain and always forward these malicious blocks to the enclave. So both delayed or fake data may trigger the enclave to disclose some secrets. So our solution is to monitor the difficulty value. We assume the attacker only has minority hash power, so it will take more time in average to generate malicious blocks. And higher average block time will lead to lower difficulty value. So if we see a suspicious drop in the difficulty value, that usually indicates that the enclave is receiving a malicious blocks. And however, the difficulty fluctuates naturally in the real world. So we cannot just rely on one fixed reference value for all the blocks. So to adjust this reference value, we group blocks into fixed-sized checkpoints. And the median value from the checkpoint 1 is selected as the reference value. And next, the minimum difficulty value is calculated based on this reference value. And we compare this minimum value with the value in the new block to determine if we want to accept the new block or not. And once there are NC block found in the front, the previous candidate checkpoint will become the new checkpoint, and the new NC blocks will become the new candidate. And the minimum value will also be updated accordingly. In order to invade the detection, the attacker will have to continuously produce at least NC blocks without dropping the difficulty value below the minimum value. And that's very hard for the attacker. But how hard is it? We calculate the possibility of the occurrence of such an event based on exponential distribution. And the result shows that for most of the parameters we chose, it will be as easy as to brute force someone's secret key as to invade our difficulty monitor. And to evaluate the number of false detections, we evaluate through all the history blocks. And although there are multiple false detections, but almost all of them are caused by either hard fork denial of service attack or bug fix in the Ethereum blockchain. So during such an event, the enclave has to be updated with the latest software. So it's actually not concerning to the application. And one existing work proposed a protocol called proof of publications. The enclave needs to generate a nonce and ask the host to publish this nonce to the blockchain. And based on the block time, it can determine the freshness of the new block. But this approach is very expensive. If we use this approach repeatedly to determine the freshness of each block, it will be very expensive in terms of time and money. That's because to publish a new block, it requires some time. So in Ethereum, we say it's around 12 seconds. And also to publish these nonce, it will require some transaction fees. So, but in our protocol, in our design, we do use proof of publications, but we only use it once at the bootstrap phase. So that the first block received by the difficulty monitor is fresh enough. And after that, the difficulty monitor, we will solely rely on the difficulty monitors to detect the malicious block. So that's much cheaper than solely relies on the proof of publication protocol. And another work called Tesseract monitors the block time. If it's higher than some threshold, it will wait for more blocks. But this approach will cause high false positive rate in blockchain that with faster block arrival rates. And it also does not prevent long-term attacks that that drops the difficulty value down to some dangerous level. So now we can securely publish and curate the data on the blockchain, but how exactly we are going to use it? Previously, we introduced a verifier to dynamically authorize new components into the system. Meanwhile, we also need to remove old or compromised components from the system. So if the enclave platform is revoked, it will fail to generate a remote attestation report. So that's not in our concern. While if the vulnerability resides in the enclave, then we need some mechanism to revoke the specific component. So like verifiers, revokers are also enclave. They are defined by the auth list. And we also provide APIs to accommodate applications needs. For example, revokers can collect votes from stakeholders, or they can directly collect evidence that prove that the enclave is compromised. And most importantly, we publish the component revocation list to the blockchain. So this ensures the high availability of the component revocation list. So in addition to publish the component revocation list to the blockchain, there's also a feature called smart contract in Ethereum. This allows us to publish executable code to the blockchain, and all the peers in the network will execute this code. One application of this feature is automated revocation. We can present some evidence to smart contract, and the smart contract will determine this evidence can prove the component is compromised or not. And if it's compromised, then it will be added to the component revocation list automatically. For instance, for a same system event, the same enclave generates two different message content. So by comparing this message, the smart contract can determine that this component is compromised. Or in other case, a private key is that belongs to an enclave is found outside of the enclave. So by comparing this key to the smart contract, we can determine that this component is compromised. In addition to auto revocations, smart contract can also allow us to enforce service availability. To determine the service quality, we use enclave to measure the request latency and throughput. And the CPU knows its number of cycles. So based on the number of cycles, it can tell the enclave a timestamp since the startup of the machine. And by recording this timestamp when the request is received and when the result is returned, we can calculate the request latency and throughput. And the client and host can sign a smart contract to enforce the service availability. The contract can define the function name, the enclave hash, and public key. And it can also define the maximum request latency and minimum request throughput. And both client and host needs to make deposit to this smart contract. So if the host violates the contract, the client can submit a dispute to this smart contract, and the smart contract will request a measurement from the enclave to determine if the host violates the contract or not. If the host violates the contract, it can seize the deposit from this contract. So our answer to the availability is using blockchain. So in conclusion, in this talk, we introduce a decent framework to provide confidentiality and integrity. We choose enclave, and decent framework uses oscillates to address mutual attestation issue, and the self-attestation issue. And we use the self-attestation protocol to lower the authentication overhead. And to enable dynamic authorization, we use formal verification inside the enclave. And to achieve availability, we combine the enclave with blockchain. And we use difficulty monitors to detect eclipse attack. And we publish the component revocation list to the blockchain to ensure a high availability of a component revocation list. And smart contract allow us to achieve automated revocation list and service level agreement. So all of these allow us to realize our decent framework. And thanks for listening to my talk, and please raise any questions you may have.